Our next speaker for this session, kicking off our technical part of our talk, is Pierre from SkyTem, again, one of our sponsors, giving his talk on high-resolution airborne electromagnetics for geotechnical investigations. Thanks, Pierre. You can get going.
Okay, thank you very much, and thank you for also accommodating me here online. I wish I have been attending in the room. That's always more fun, but this will be my talk for today. Will be on this platform. So I am going to talk to you today about high resolution airborne electromagnetics for geotechnical investigations. And what we see here is the outline of the talk, and where we will focus on what we call the SkyTem diamond. And what we see here is that it's the platform down here, the very small airborne electromagnetic system that we will go into some details about. We will also talk about what can we actually use to carry this platform with either a drone or a helicopter. And then we will show some of the first results and case studies. And at this stage, they are both based on some Danish investigations. So what is it we have done here? You can say it is really with a plan to shrink a system to get a more surface near high resolution of an airborne EM system, and also be able to utilize it by both smaller helicopters and drones in order to also give a price competitive alternative. So the more technical details of the system as we see it here is that, so it's an airborne EM system with a transmitter loop, again running all around the diamond shape here on that central loop. And the area of that platform is 17.7 square meters. So a very small system that we have here, and we will have the receiver coils, and we have all of the other electronics placed here in the front part of the frame. And the combined weight of this complete system is just below 50 kilos. A little bit more on it is, you can say that through the iterations of the development of this system, we started out, you can say, in this single turn transmitter configuration of the 70.7 square meters to transmit 165 amps, but it's been increased to the 250 amps, right? So we will have a transmitter moment just around 250 times nearly 20, so just below 5,000 NIA is the transmitted moment of this system that we put out. We run with a very high base frequency, again started out with 75 Hertz repetition, but has now a repetition rate with very short time pulses of 325 Hertz, again to get a very large stack size in a limited time of interval to get a good signal to noise ratio, just also combined by the stacking. And then also, as we can see here, that even though we actually increased the current with nearly 100 amps, we are still actually having a quicker turn-off ramp of the system, again helping inducing the system and giving us the early time data that we had on the original system, because we have this much higher turn-off rate of the actual current. So that's sort of like really the base technicalities of the transmitted system here on this diamond platform. And what is it that we do? As we can see, this is, and what benefits can we actually take away from this system, or what was the driving forces actually for developing this system? And we can say, so it's this fully airborne TEM system, so with both the transmitter and the receiver on the platform itself. It can be operated by the drone, as we see here, but also by smaller scale helicopters. So, and what we do deliver with it is high near-surface data quality compared to both ground-based and other airborne TEM systems, right? It can map close to buildings and infrastructure. It has an easy mobilization, so typically actually to build the system takes only about around half an hour. Then we have the fully operational system, so it can easily be deployed out. It accounts for fast mapping of small to medium-sized areas. Typically, acquisition speed is with the drone around 10 kilometers per hour, on the small helicopters up to around 35 kilometers per hour. Compared to ground-based system, of course, it has this big advantage that we can do all-terrain mapping, so we can go over wetlands. And again, if you are over farm fields, croplands, you don't damage the crops, so you can also fly over farmland without having to do any sort of compensations, and it can operate all year around. So what do we expect for the system, or what have we seen from this system? We have seen that we can map from the surface in a sub-meter scale resolution at the surface and down to depth of around 100 meters. And it's very flexible, so fully airborne, no really ground contact needed. So again, limited or non-invasive in any art, and it can, it's flexible, so it can have been flown both on the helicopters or drones. It would also mean that in this all-terrain access, right, that we can also go into polluted areas, for instance, and things like that, just flying over it without having to access the ground and take all of these risks into it. And because of its limited size, of course, it also gives some possibilities to fly at higher altitudes where normal scale heavy systems cannot fly. And it's, as you say, very operational agile. It can be rapidly deployed. It's easy to transport, so everything packs together in these rod lengths, right? And as I said, it can be assembled and tested within a single hour after arrival to a test site. And just to say, how does it look? We can operate it as we see here, underneath the helicopter or underneath the drone. So the system is completely self-sustained, so the actual carrier doesn't affect the data as such. And we also see that the tow length cables we have for both platform is also long enough, so we don't see any bias for any of the carrier platforms going into the data. The drone, to focus on that first, we use as the carrier drone is a Hector drone. It's a sort of like a hybrid drone, meaning that we have the 6 electrical motors driving the rotors, but the power for the electrical motors is a gas-powered engine, right? So in that way, it's this hybrid thing. This drone can have the up to 50 kilo payloads as the system is weighing. We can fly 35 and going on to 60 minutes flight time on the drone with the system underneath it. At the moment, we have to operate within visual line of sight when we fly it with the drone. So that would mean a maximum of 500 meters away from where the operator is placed, and at a distance closing into 65 meters from any infrastructure. And this is based on the flight rules pertaining in Denmark and Europe, where we have the operational permits from the Danish Ministry of Transport, so that we are actually allowed to operate this drone system in Denmark, and that can be transferred at further stage to all European countries. We have test flown it in Sweden and Norway, so right now in the Scandinavia, but of course also bringing it to South Africa and overall the African continent. There are also still some flight permits issues on the drone legislation that would need to be transferred. And in a way to bring the Diamond platform maybe earlier out and easier out, we have then also now shifted. So just here, now let me just stop before I go into that. Here I will just start this video where we see the Diamond system flown by the drone in action. So here we will see how it actually looks when we are surveying with the system. Yes, so there we saw sort of like the thing in action here. And just as I was about to go into, because there are some of these legislation issues to getting the permits to fly with drones in different countries, we also say, okay, to actually bring the measuring method, the diamond, maybe earlier out to the market, and also if we are requiring to fly larger survey areas and we are still limited to this visual line of sight, we then also said, okay, can we also put this system below a helicopter and still get the good data? And of course, in a benefit to the larger system, we will have the smaller helicopters that can lift this 50 kilos payload. So there is a wider range of helicopters available to also operate this system that we can utilize. And that has been now also then flown and tested, as we see here, under the helicopter, again, both on an actual test range in Sweden, but also in 2 semi-commercial surveys in both Denmark and Norway, as we acquired data now with the diamond being carried by a helicopter. Okay. So if we now then switch, as we had the technical introduction here, and we will then go into looking at some of the results and 2 case studies here from where the data has actually been acquired with the diamond system. And the first one here is placed in the central part of Denmark. The locality is called Øbakker. We've seen the flight path here. And the purpose of this, you can say, was really surface near mapping. It was a thing where you would actually like to map the peat thickness of this area, right? And the scope of mapping the peat thickness in these areas in Denmark is that these are former wetlands that has been transferred into farmlands. But in order to avoid the decomposing of the peat and thereby the release of CO2 to the atmosphere, there's actually a plan to then re-wet some of these farmlands. And in this case, then we will also need to pay some compensation to the farmers. So in order to bring all of that into aspect, we needed a precise measurement of these peak thicknesses in this area. So we flew along these lines and just we'll start a short film here where we will see how we fly along the line. We have all of the individual measurements showing up in this plot over here. They will then be plotted along the line we are flying in here, and we can see how it goes into the inverted results in the top as we fly along the line here. So we see how we see variations in the signal strength, corresponding also to flying over the highly conductive areas here and coming into the resistive payments. And what we really see, these top conductors, we will see here, we will see some more fixed examples and comparison with ground-based data on the next slides. But these are really the areas where we have the peat. So what we are mapping up here is the peat thickness. And just also watch that this is for a total of a 30-meter depth interval. We do see deeper, but it's the variations in these top layers that we want to see, and how we actually see variations down here in the sub-meter scale being mapped out by this system. And then we now are looking continuously on these 2 profiles marked A and B here, with the A profile being the top and the B one. And then we will switch in between looking at the airborne diamond data and then on some ground-based data collected with the TOTEM system. And again, we see the 2 lines here. We see the sand lens, we see some peat on the top, and we see some more conductive lower material here with some more clays and sills coming in here. And these were the data from the diamond system. And here we then have the 2 same lines, you can say, or as closely overlapping as possibly, based on then the ground-based TEM data. And overall, of course, in these 2, we see the same structures. We see the sand lens here, but we also see there is a tendency to a sort of like more thicker layers in the top for the for the PEEP, where they are more confined here in the airborne data. Then if we zoom into just looking at the top 10 meters, again focusing on this surface near resolution that can be used in many kinds of settings of geology, we again see for the ground-based data, sort of like this diffusionness over 40 or 4 meters of this more conductive space in here, while it's very confined in just the top 2 meters here. And in this area, there has also been you can say actually ground testing with driving metal poles into the ground to actually find the resistance from when the peat stops and you go into the sands. And that corresponds very well with the data that we collect here on the airborne diamond data. Also, another support for having it as this very defined area here open in the top meter is that there's also along these lines, we have ground-based dual EM frequency domain data as well that corresponds into the diamond data, thereby validating our methodology here that it should work properly. And just then as sort of like a sum of what could actually be some of the resolution. If we here look solely on the diamond data, and we can see what we can do is that we can gate 4 here is just about saying that that's utilizing data from 4 microseconds, from 6 microseconds, or for 9 microseconds. So if we just remove the early tide information, we see how this structure here become more diffuse. So it really highlights the importance of any TEM system being ground-based or airborne, that utilizing the very early times is what gives you your surface near details, and that's what we can obtain with this new diamond system. Jumping on to the second case here. Oh, I think I'm more or less on time, yep, sorry, but it should be quick. This is a contaminated site, again, a hard to access area that we are coming into. And the area was flown. We see sort of like the overview here. We see how we have all the infrastructures and buildings around, but we can fly everywhere just around it here with the diamond system. Again, we see the correlation and also the overlap, and very good between the ground-based and the airborne data here, right? And what really was the case is here that there's been an old landfill site over in this area here where you have had contaminating coming into the groundwater reservoir following this sandlands that we have here in the area. So it really is mapping the structure of this sandlands. That was the scope here. And also again, then just in the horizontal place, we see the same thing here from the ground-based data and from the EM data, and we can see how we define the top here very, very nicely. And that's it. So I'll just leave this as the sum up as the time has run out here. Thank you very much for your attention.
Awesome. Thanks, Pierre. All right. I think we have time for one quick question. Is there any questions for Pierre on SkyTem? I'll just use the microphone so Pierre can hear you.
Thank you. I'm Belinda. So from the presentation, I saw we have a helicopter or a drone carrying something. The equipment is down. So
yep.
If I'm surveying my line from south to north, and we get wind blowing from east to west, so how is that data going to be accurate? Because this wind is going to blow the equipment away from my line.
Well, just get a picture of it closer on. You also saw the video where we are flying, and of course, because we have the speed, we will have something that we will drag it along the line, right? Heavy crosswinds, yes, it can be shifted slightly offline, but the line is not that long that it will, and also there is limited drag, and there is also some navigational winds on the system. And in addition, of course, there is a GPS receiver and a laser giving us the exact position of the frame. So it could be that, yes, maybe the system will fly a meter or two offset the planned line in very strong crosswinds, but we will know that it's there. So compared to then the resolution and the footprint of the system, it shouldn't affect what you want to see.
Awesome. Thanks, Pierre. Just one more question, Pierre. Let's just get the mic to Jeff. Okay.
Got my voice carried. Here we go. This is for geotechnical mapping, in which budgets are quite often fairly limited. If you take something like a 500-kilometer survey, could you hazard some kind of educated guess as to what the cost would be in US dollars per line kilometer?
Yeah, I think it's very early, and we of course and we would, if we then say 500 kilometers, we would most likely go with the helicopter to cover it within a reasonable time span and not moving too many operational sites with the operator, right? And then of course, typically you could say these small helicopters is more accessible, so you should be able to keep still mobilization down. Also, they are typically around half the price per the hourly rate than the traditional helicopters you use for airborne EM, right? So being, again, country specific, giving exact price, I would expect a price range between $50 and $100 per line kilometer.
Did I hear you correctly? $50 to $100 per line kilometer?
Yeah.
Okay, thank you.
Awesome. Thanks, Pierre. I think we're going to close it off there. Thanks, Pierre and Christina, for a great presentation. And thanks again for your support.